Hi, my name is Nuno Vasconcelos, and it is a pleasure to be here to tell you about our work or our recent work in contrastive learning. So just for the sake of completeness, I'll start by doing a brief review of contrastive learning. I assume this is known material for most of you, but just to set the notation. In contrastive learning, we're given an image xi and a model or embedding f. We start by computing a pair of augmentations of the image, P and Q, and those can be obtained by operations like rotations, changes of color, crops, and so forth. And then these augmentations are fed through an embedding, as shown here in this picture, where we have three images, red, green, and blue. We compute an augmentation for a pair of augmentations for each image, and then they are run through the embedding. And then we use these embeddings to optimize the contrastive loss. So the embedding is learned by optimizing this contrastive loss, which is a loss that encourages closer embeddings for augmentations from the same image, which we call the positive pairs, and distant embeddings for augmentations from different images, what we call the negative pairs. So in our example, positive pairs are augmentations from the same image, so they have the same color, and they are close to each other. And negative pairs are embeddings, of different colors. So augmentations from different images, and they tend to be farther apart. Now, as you know, contrastive learning has been quite successful and is approaching the performance of supervised learning, but there are still a number of open issues, such as how do we choose good augmentation? How do we mine hard negatives? So usually there's a very large number of negatives that are available in the data set. How do we choose the best one? How to avoid iconic matching of image pairs and sort of move on to more abstract groupings with better generalization. So right now we're considering two augmentations of an image as positive and two augmentations of another images as negatives. But for example, if you have two images of dogs, they're going to be considered negatives. And so we would like to move on to a setting where sort of all dogs are positives and dogs versus cats are negatives. But of course, because we don't have labels, this is hard to do. So the question is like, can we encourage sort of more abstract groupings? And finally, how to guarantee robust learning when these judgments of positives and negatives are noisy, again, because we don't have labels. So I'll start by discussing a little bit our work in the area of augmentations. As I'm sure you know, the standard augmentations are handcrafted. Again, rotations, changes of color, crops, and so forth. So the question that we asked was, can we produce optimal augmentations that are optimal in a well-defined sense? And in order to do this, we borrowed a page from classification, where adversarial examples are frequently used to do what's called adversarial training, which is, they're optimized to challenge the network and increase its robustness. So I'm sure that you all know what adversarial examples are. So the classical picture is shown here. We have an image of a panda that the network classifies correctly. But then we had a very small perturbation, which is perceptually undistinguishable. So the image looks the same, but this perturbation is enough to make the network predict a different label, hence the name adversarial. Now, these adversarial examples can, in principle, be also used to increase the robustness of the representations learned by contrastive learning. So in order to do this, we have proposed a method that we call contrastive learning with adversarial examples. And it's quite simple, the computation of these adversarial examples. So given an augmentation Q, we find a second augmentation R such that maximizes the loss, the contrastive loss with respect to the original augmentation Q. And as usual in the adversarial example literature, this augmentation is constrained to be in a small neighborhood, an epsilon ball of the original augmentation. So the perturbation has to have very small magnitude. Now, these perturbations can be computed with any adversarial method available in the classification literature. In our work, we use the fast gradient sign method. And this leads to a very simple procedure. It basically, given given the augmentation, we propagate the augmentation through the embedding, and then all that's needed is to back propagate the gradient of the loss, the contrastive loss, through the embedding in order to compute this perturbation delta, which is added to the original augmentation to compute the adversarial example. As common in the adversarial defense literature, the embedding is then trained with a loss function that combines two augmentations. The first is a loss that based on a standard augmentation, say, for example, image rotation. And then the second is an adversarial augmentation with respect to this original augmentation that is computed with the method that I've just summarized. As also frequently known in, as also known in classification, there are some tricks that make the learning more stable. For example, we find it to be useful to use a separate batch normalization layer for a clean and adversarial examples. So this is equivalent of thinking of these adversarial examples as coming from like a slightly different image domain. But once one uses this trick, learning is very stable. The performance of, so these adversarial examples can significantly enhance the performance of contrastive learning. As usual, we present results in terms of the downstream classification task. You can see here the results of classification accuracy. So the green is a baseline, the standard contrastive loss method. And blue and red are two variants of clay with different parameters. So these are slight variation that I will not discuss here in detail. But the most important point is that these adversarial examples enable significant or non-trivial gains in performance over the standard contrastive learning. These gains hold across several contrastive learning methods. So we've tried this on various contrastive learning methods. Here I show results for the plain contrastive loss and SIM-CLR, but we've also tried the MoCo and other methods, and you can find more details in the paper. And these results, the gains are very stable across methods. They're also stable across architectures. And in fact, what we found is that the gains tend to increase with the size of the model. So that's shown here for the ResNet architecture. So for the ResNet 18, we have a gain of about 2.5 to 3 points, which is non-trivial. But as you can see, as the size of the network increases, the gains increase. And by the time we get to the ResNet 101, the gains are quite substantial. And so this suggests that these adversarial examples are particularly useful when there is a need for better generalization when we use these very large models. Okay, so this addresses the optimizations of augmentations. The second question is, how do we move beyond instance matching? Can we force matching at a higher semantic level? Ideally, like I said, we would like all dogs to be positive and cats to be negative, but we don't have labels, so we can't just do that. Is there another way that we can force groupings at sort of a more abstract level than just the same image? And in order to do this, we're going to try to leverage a property of human reasoning, which is the ability to match signals of very different nature. So in order to illustrate this, I'm going to show you a bunch of videos, and only one of them will have sound. And I'm going to ask you to think about, like, what is the video that is associated with that sound? And I think that for most of and I think that for most it's actually hard. This sound is associated with this man playing guitar. And that's because we have the ability to sort of match signals across very different, across these modalities. So there's sort of we match signals at a more abstract level than just, pixels or sound volume. And so we try to replicate this ability by asking the question of, can we learn similar representations by using audio-visual instance discrimination? And so the idea is to do contrastive learning across modalities. So rather than defining positives and negatives as two augmentations, two image augmentations, we use different modalities. And so we have pairs where one element is audio and another one is video, and the task is a much more challenging task. So the network has to learn to match one audio stream to a video among a collection of videos, or it has to be the opposite. So it has to match one video to the corresponding audio amongst a database of audio streams. Because this matching has to happen at a much higher level of abstraction, this should lead to better generalization. So, for example, once the network is able to make these matches, because dogs barking produce similar sounds, so it should be able to connect two videos with two very visually distinctive dogs, just because they are producing this similar sound. So the implementation of this is sort of conceptually straightforward. So we just replace, the contrastive laws with a version where now instead of, again, augmentations of the same image, we have pairs of video and audio features. So we have, two embeddings now, one for audio and one for video, and the video feature vector is matched to an array, a bank of audio feature vectors, while the audio feature vector is matched to a bank of video feature vectors. And this is how we define positives and negatives. So the corresponding audio is declared positive, and then the other audios are negatives for this particular video. Now, one of the advantages of AVID is that once we're done training, we immediately obtain representations that can be transferred to a larger set of tasks. And in fact, our video embedding can be, for example, transferred to a task such as action recognition, while the audio embedding can be transferred to a task such as sound classification. And what we've shown is that, or what we observed is that this cross-modal supervision enables the learning of strong representations. And this is illustrated by this figure here, where I show the performance of 3 different training techniques. So cross-modal supervision, AVID, versus within modal supervision, where audio is matched to audio and video is matched to video, and joint supervision, where we combine two. And sort of the interesting property here is that the cross-modal, so these are the top are the video-based action recognition results on kinetics, and the bottom are audio event recognition accuracy. And we can see is that the cross-modal approach, which is shown by this orange bar here, outperforms the other 2 approaches by a significant margin. And this, we believe, is because when there's, the matching can be done within the same modality, which these 2 approaches allow. It's much easier for the learning algorithm or the representation to cheat. So because it can map a video to video, we can just sort of match pixel colors and things like that. But when the matching has to be made strictly across modalities, it really has to sort of learn, abstract away these higher level semantic representations that bring together audio and video. And this leads to, a stronger representation that generalizes better. So here are some examples of the clusters that are learned by AVID. So these are embeddings of many videos, and here we show the results of a query task. So the videos on the left are the query videos, and then there's like the top 4 matches, and here again 4 more query videos, the top 4 matches. And what I would like to sort of, what is interesting here is that, as you can see, the video matches, the system is able to match videos that have very different appearance. And again, this is because it's doing the matching at this sort of higher level of abstraction, which also includes, the sound, for example, that these runners make as they run. So that's, moving up the semantic ladder. A third question is the question of how to, what are good positives and negatives, and in particular, how does one avoid false positives or negatives, and how does one deal with them? What is their impact? And maybe here I should say a little bit more what I mean by this. So false positives are pairs of video and audio that are not mutually informative. They were just grouped by chance. So here's an example. this case, the audio is totally unrelated to the video. Here's another example where basically there is no audio. And so we call these false positives because, you know, they're pairs that are just random. They don't really mean anything. They were just created by accident. There are also, like, as you know, contrastive learning methods. There's also the risk of false negatives. For example, if you have two videos of somebody playing guitar, because we don't have labels, these are considered negatives. But of course, these are false negatives because, you know, the videos are basically about the same subject. And so in order to analyze the impact of negatives and positives, we sort of did a study where we started by looking at the impact of false positives by artificially injecting false positives in our data set, and then training two models, one with the entire data, which is shown here in green, and another one where we, you know, filtered away these false positives. And you can see that when the false positives are introduced, the performance degrades considerably. So these false positives can harm the learned representation significantly. So in order to reduce the impact of false positives, we propose this weighted contrastive learning loss, where you know, each example is weighted according to the similarity score between its audio and video. And so here is an histogram of our data set of the similarity scores between audio and video. At the top here, closer to 1, there are examples, you know, where the audio and video are very well matched. So there's a weather forecast video and there's a person talking about the weather. And then as we move towards the right, we get to sort of more mismatched pairs. So all the way here at the end with a very low score is a video where there's a person playing drums, but then the audio is just static noise. So it's totally unbelievable. And again, you know, this is the histogram of scores throughout the data set. And so what we did is we use these scores to define the weight for the loss of each example by using as a weight function the cumulative distribution function of this score distribution. And so that means that examples with very high similarity, with very high score, receive a weight of close to 1. Examples of very low similarity receive a score close to 0. And of course, high and low similarity are defined with respect to the data set. So they're adaptive with respect to the data set. And our experiment shows that this can make a significant difference. So here is the same plot that I showed you before, but now in yellow is the curve of the representation learned with this weighted contrastive loss. And you can see that it outperforms even the oracle, even the method where we threw away, like the red method, where you know, the faulty positives are ignored. And this is, of course, because we're only throwing away the faulty positives that we artificially inserted in the data set. But the data set already had false positives as its own. And the fact that you know, the contrastive learning loss outperforms this significantly shows that it's able to successfully discount the negative false positives, the false positives that were already in the data set. Now, a similar analysis can be done for false negatives. And you know, it can be shown that they're equally harmful, but I don't really have time to discuss this in detail. So I'm just going to skip about sort of the you know, what we have done. So we've proposed another loss function to deal with this, and I'm just going to show you the impact of these robust loss functions. So here is the performance on the UCF classification on action recognition on the UCF data set of AVID, the standard audiovisual instant discrimination. Here's the performance with the loss that accounts for false positives. Here's the performance of the loss that accounts for false negatives. And here is the performance of the final robust AVID system that includes these two losses, and which, you know, as you can see, leads to significant, you know, a very non-trivial performance gain. And by the way, all these methods are superior to the state-of-the-art, you know, the previous best approaches to this sort of audio visual instance discrimination in the literature. Okay, so I'll finish here. So deep learning has unmatched performance in many vision tasks, but you know, this is so far mostly in the supervised setting. Contrastive learning is a very exciting alternative, but like I discussed, there's still a number of open questions. And we have shown that non-trivial gains are possible by optimizing rather than crafting augmentations, forcing matches at a higher level of abstraction, namely by matching across modalities, and accounting for false positives and negatives by introduction of robust losses. Unfortunately, I won't be able to address any questions today because I'm traveling. But if you have any questions, please feel free to email me. Thank you very much.